Just have a pen there. Just grab the attendance here. You control. Oh, well, I can stretch too. Right, Michelle? She was, yeah, okay. Abir? Autumn? Celine? Sophia? Mubarak? Shadira?
Yeah.
Mohammed? Sabrina? Moza? Angela? Ahmed? Safra? No, okay. Neil? No. Mahmoud? No. Gafar? Amjad? Zara? Mo?
Yes.
Daniel? Sebi? Sabrina? Elfrida? Aria? Judy? Yumpang? Amna? Mariam? Mariam? No. 1, 2, 3, 4, 5, 6, 7 people absent. 1, 2, 2 people late for the first class. Not great. Not great. Here you go, Mo. Thank you.
Sir, question for number 4. It says, what is the probability that a non-smoker would drink? So does that mean that non-smoker given that drink? Something like that.
Yeah. What's the probability that a non-smoker would drink? So you're given that they're a non-smoker. Yeah. Yeah.
What's the sign for R? A or B?
Union. Yeah, we did this last week. Didn't we?
Yeah.
All right. Okay, let's continue. So like I said, the next lesson is it's pretty straightforward. It's just really a couple of definitions. So we can say, well, maybe you know this from the word, A and B are mutually exclusive. So what does that mean if you say 2 events are mutually exclusive?
They're separate?
Not necessarily separate, no. Not quite that. Yeah? No? Do you know this word from English, mutually exclusive? This isn't like some teenage sitcom or something. Like, this isn't A saying to B, can we be exclusive or something? You're like, no. No, that is so not it. Right. A and B are mutually exclusive. Does anyone have a real answer? Say again? Yeah, so what would that mean for probabilities? Yeah, but everybody's dancing around the point.
They don't occur at the same time?
Yeah, so what's that as a probability? Okay, you're making heavy weather of this. Its probability of A and B is 0. Simple. They're mutually exclusive, meaning you can't have them at the same time, like you said. Or what you were trying to say about they're not overlapping, occurring. So just simply, as a probability, it means that A and B is 0. So on the Venn diagram, would have to have a 0 in the middle. That's what it means. Mutually exclusive. It means you can't have A and B occur at the same time. Yeah? Yeah. Now we haven't really seen examples of this. You know, in all our examples we've done, it's possible that you could get A and B at the same time. You know, if you flip a coin and you roll a die, the probability of getting a 6 on one and heads on the other, you know, that's not 0. That could happen. Okay. So that's mutually exclusive. So that's okay. And then the next one is A and B are independent. Right. So again, just like with mutually, now don't give me a silly answer, please. A and B are independent. What might that mean? It means A don't need no B, is it? What is it? Yeah, I know, I can see that.
A or B is 1 or 0?
No. Think about what the word might mean here, independent. Say again? Yeah? What about it? Started off well. No. Yeah, that's the idea. So how can we put that as a probability? No.
Probability of A
Yeah?
without B.
Yeah, go on. So far so good, you're right, yeah?
Okay, so B dot.
No. Started off promising, not this. No. So, one way to think about it, but it's not the way we'll actually use, because it's more convenient another way, but as an idea you could say A and B are independent, meaning that the probability of A happening, given that B has happened, that should be the exact same thing as the probability of A happening, given that B has not happened. In other words, regardless of whether B happens or not, it has no effect on whether A would happen.
Can we say B is 0?
That what 0?
B?
No, not necessarily. So again, let me give you an obvious example. If you flip a coin and then roll a dice, the outcome of the coin and the dice are independent, right? It's not like getting a heads or tails first has any effect on whether you get a 6 next, right? So this is actually a common situation, that the B has no effect on the A. Now this formula, we can actually simplify it. Can I scroll down a bit? Yep. So using our formula from the last class, this is the probability of A and B over probability of B. And this one here, A and not B over probability of not B. Yeah? Is that okay so far? Now we can simplify this a little bit further. So it might be helpful if we just draw a Venn diagram here just to have a picture of what's going on. There's A and there's B. Okay, I don't like the knots here. So let's take care of the first easy one to take care of. A and B over probability of B equals, so what could I replace this with? Probability of not B.
1 minus
1 minus,
PP.
yeah, probability of B. Okay. Now I'll just give you a minute. I want you to really think about this. What could we replace the top here with? So just have a look at the Venn diagram. See if you can do anything similar to what you did at the bottom here. Okay, so A and not B. I'll help you out here. A and not B. That's this here, isn't it? Yeah. That's this here.
So 1 minus B.
Not quite. Nearly. Nearly.
Probability of A plus probability of B.
No. You're heading away now. No, I want to try and make it simpler. Simpler. Probability of A union B minus, yes, probability of B. No, that's simpler because it doesn't have not B in it.
Sorry.
Yeah.
Can you say probability of A minus probability of A intersect B?
Okay. Probability of A minus the probability of A intersect B. That's fine. That's fine. That's actually what I was going to do on the next line, but since you've spotted it, I'll skip a step and just go straight to this. Right. So let's rearrange this and see what we get. Let's clean this up a little bit. So this is probability of A and B times 1 minus probability of B equals probability of B times probability of A minus probability of A and B. That's an A there. Right, expanding. Probability of A and B times 1 minus probability of A and B times probability of B equals probability of A, probability of B, minus probability of A and B times probability of B. Now I know that looks messy, but something really nice happens. There's a cancel in here. If you can see, something cancels. Yeah, can you see this guy here? Is the same as this guy? So they cancel, and you end up with the result that I wanted. Another way to say that A and B are independent is this. A and B are independent if the probability of A and B is equal to the probability of A times the probability of B. That is much easier to deal with than that. But it means the same thing. If you calculate the probability of A and the probability of B and multiply them together, and you get the same as the probability of A and B, then we can say, therefore, A and B are independent. So in other words, this is a way to check, if you like, if A and B are independent.
So we can be asked to find if they're independent, and then we just do this.
Yeah, if you know they're independent, you can use this formula. And if you're asked to check if they're independent, you can see if this formula is true. So look, we'll have a look at some examples now that we have these two ideas done. So, can I scroll? No. Okay, can I scroll down? Okay. So, here's my question for you. You can try this and give me an answer. is actually just the first question here. In a group of 8 people, what is the probability that they will each have a birthday on a different day of the week? So what's that? What is it? 7. 7 probabilities. I don't even know what that would mean. Come on, I'm not getting any answers here. 0. Why?
It's 8 people.
There's 8 people and there's 7 days in a week. Yeah? So this probability is 0. Okay. What's the probability of winning gold and silver at the same time? 0. Why? Because gold and silver are mutually exclusive. Winning gold means automatically you don't win silver. And winning silver automatically means you don't win gold. So, they're mutually exclusive. Probability of winning gold and silver is 0. You draw a card from a deck of 52 cards. What is the probability that it is a heart and it is black? 0. Again, because they're mutually exclusive. You can't be both a heart and black in a deck of cards. Yeah? Okay. Let's jump down a little bit. Let me make up now. So they're kind of silly examples, but let's make up like an interesting science example. So, suppose you're looking at illnesses, and you notice that you're looking at your group, and perhaps we'll say 2% of people have some illness. We'll call it A. And let's say 3% of people have an illness. We'll call it B. And we see that 1% of people have both A and B together. So if you look at your population of patients, 2% of them will have A, 3% of them will have B, and 1% of them will have both. So an interesting question you might want to ask is, are A and B independent? Now obviously that's a very important medicine question, because if the answer is no, then it means there's some interaction between the two diseases, that having one influences whether or not you have the other. Maybe having A makes you more likely to have B, or maybe having A makes you less likely to have B. But this is an important question, I think we can all agree, right? If they were independent, then if there's no interaction, then you can treat each disease separately. But if there's some kind of interaction, then perhaps there's something else to look at. You know, perhaps there's a third reason you might get both at the same time. So for example, one example might be heart disease and diabetes. So do you think those are independent or not independent? What do we think? Not independent. That there's some interaction between the two. And there is, because often people who present as overweight, that could be a cause for both diabetes and heart disease. So they're not independent because we actually can see something that's making the two likely to happen together. Okay? So let's use the formula to test it. If they're independent, the probability of A and B should equal the probability of A times the probability of B. So what's the probability of A and B? 0.01. Does that equal 0.02 times 0.03? No. So then,
It's
not independent. So then A and B are not independent. And you can see that was a very, very simple way to check if they were independent. Right? I mean, there wasn't any mad complications here. We simply had to check if A times B is equal to A and B. And that's all. So you can see why this is a useful formula to know. So you see this type of problem a lot in science. You know, you have two things and you want to know if they're independent. So let's see. Maybe I'll do... No, I won't. I won't do a controversial one. That's okay. I'll be good for now. I'll be good.
Do it.
No. I won't. Maybe next time. Okay, so just for a couple of minutes, you can see these questions are really short. Like some of them you can answer within a couple of seconds. So if you can just try these for 5 minutes then.
Sir.
Yeah.
Regarding the coursework.
Yeah.
Can you show us the format you wanted?
What do you mean?
Like
Typed up?
no, you showed us how to type.
Yeah.
Like how.
Well, Colin gave you a checklist, didn't he?
Yeah.
Yeah.
Same as that.
I use the same one in physics, and that's perfectly fine for maths as well.
Times New Roman, all that.
Yeah, all that's fine, yeah. So use...
Double space.
What's wrong with that?
This formula.
Ah. Is double space a problem?
Yeah, because it'll like when you go to the next line, it'll be like a huge space.
Yeah, okay. Well, to be honest, I'm not too fussed about the double spacing. It's the thing that really bugs me is the font and the size. Sometimes students use stupid font and stupid sizes. That's the thing that annoys me the most. You know, Arial 16 or something. No. Yeah.
Is it possible to give us a question in which they give us the probability of A and they give us the probability of B, but they don't give us the probability of A and B, and then they ask us to find if it's independent.
There must, well, that's possible, but they would have to provide a third piece of information. Because if you just know A and B and that's it, it's not possible to decide. So if they don't tell you A and B, then they have to tell you something at least like A or B.